All right, well, get ready for a roller coaster of a lecture because we're actually going to talk about roller coasters. So, which is an example of circular motion, not horizontally, like we talked about last time with like the air hockey thing and the with the string on it. Now we're going to talk about circular motion in the vertical direction with gravity pointing down. Is what we're going to talk about today. So there's a couple different ways of thinking about it. Last time, just to review, again, we talked about things in the horizontal direction. We talked about the difference between centripetal and centrifugal force. Talked about the acceleration being v squared over r. And then we did the worksheet on centrifuges last time. So just to kind of review what we've been talking about, I like putting up this slide just to emphasize that there's I can give you one thing, I can give you RPM, and I expect you to find angular speed and period and frequency and all these things, acceleration, so on. So the angular speed, some people like to say this is a W. Technically, it's a Greek symbol omega. And this is the change in angle, the change in time. Specifically, the angle needs to be in terms of radians, not degrees. And so, as a result, this has units of radians, this has units of seconds. So the units of this is radians per second. The next thing is the frequency. So the frequency is the number of, not the number of radians per second, but the number of cycles per second. And so each cycle in one circle, there's 2 pi radians, right? And so if you take the radians per second and divide by 2 pi, you get the number of cycles per second, which is also referred to as hertz. So as I said, angular speed divided by 2 pi. Sometimes I call this angular velocity. Different names for the same thing. So there you go. That's the frequency is the angular speed divided by 2 pi to get cycles per second. Now the period is the number of seconds per cycle. And so if we just take 1 over the frequency, that should give us the period. Or in other words, if I write the period is 1 over the frequency there. And because we know how to relate the frequency to the angular speed, that means that the period is also 2 pi over omega, right? Because I can just sub this into here. Okay? The next thing I believe is the velocity. And the velocity is always, the distance over time, right? And so if you're traveling in a circle, you're probably moving some circumference in some amount of time. So the circumference is 2 pi r, not pi r squared, but 2 pi r. Right? Pi r squared has an r squared that has units of meters squared. So that's an area. But the circumference is 2 pi r. And then the amount of time it takes to do one cycle, well, that's just the period. So you can divide by the period like that. And units are just meters over seconds, meters per second. Now, a cool thing that you can do, and part of the reason why physics nerds like to use this omega symbol is that you can write this down, and then 2 pi over the period works out to be omega over 2 pi. The period is, if you sub in the period is 2 pi over omega, then the 2 pi's cancel, and 1 over omega equals r omega. So again, part of the reason why we like writing things this way is this looks very elegantly like this with an r omega, which is nice. And then finally for the acceleration of anything moving in a circle is v squared over r, as we talked about a couple lectures back. So you can take this, v equals r omega, put that into here. The r's partially cancel, and you end up with r omega squared. Sometimes this is the most useful thing to do. Other times maybe you want to focus on that form. Anyway, the units of this thing are meters per second squared, as all accelerations are. And so if I give you one of these things, you should be able to get to the other ones, right? If I give you a period and the size, you should be able to tell me the velocity, so on and so forth. If I give you the acceleration and the velocity, you should be able to tell me the radius, so on and so forth. All right. So here's some new stuff. Circular motion in the vertical direction. I don't know why it's necessary for me to have a video of someone rotating something around in a circle instead of doing it myself, but here it is. And so this is the kind of motion that we're going to think about today. There's some kind of a string here. There's a ball in a string. Maybe we want to know what the tension in the string is. Maybe we want to know how fast you have to swing it before it starts to, not be able to, it's not going fast enough to get through it. These are the kinds of questions that we might want to answer. Now we could assume that it's constant speed. We could pretend like, oh yeah, we know that the velocity is whatever it is, and it's going the same speed at the bottom as the same as the top. Not quite true, right? It's probably going a little faster at the bottom than the top, as we'll talk about. So we could approach it and say, well, we don't really know the speed, and look at it that way. But in any case, the force diagrams are the same, and a lot of the analysis is the same. But part of the reality here is that, when you actually are spinning this thing, you probably are giving it a little bit of a tug. And so you could just sort of hold it fixed and not tug it, in which case the speed would not really be constant. But if you do give it a tug, maybe it's, I don't know. But there's more than one way to think about it. But the force diagrams are the same, which is the nice part, which is what we're going to do right now. So let's say that we want to calculate the tension. We've got our ball here. So what are the forces that are acting on the ball? Where there's as the ball is going from here to here. Well, there's the weight and the tension, right? So there's the tension from the string, and there's the weight pulling down. So that's fine. There are no forces horizontally, even though it's moving horizontally, and the velocity is towards me. That doesn't mean that there's any forces horizontally, right? So these are the two forces there, and they sort of are going in opposite directions. And so I can sum the forces in the y direction, or let's say sum of the forces in the radial direction, and the tension is pointing towards the center of the circle, so we can say that that's positive. The weight is pointing away from the center of the circle, assuming g is plus 9.8. And the difference between those two forces equals the mass times the acceleration of the thing. Now we know this ball is moving in a circle, which means that anything moving in a circle has an acceleration of v squared over r. And so if we wanted to solve for, so anything moving in the circle has an acceleration of v squared over r, so we can actually use this to figure out what the tension is, right? Because if we know what v is, we know what r is. The only thing we don't know is the tension. So we should find this. In other words, if you put a scale on this string, the scale should read this. And just in terms of reasonableness, does this equation make sense when the thing is standing still? Well, if it's just sitting there, and there's the tension and the weight, and it's not accelerating, right? mv squared over r, if v equals 0, that's going to be 0. If it's just sitting there, that tells you the tension is equal to mg. Is that reasonable? Yeah, that's pretty reasonable, right? The tension is equal to the weight. But if it is moving, then the tension is going to be more than that, right? And sure enough, if you make a v non-zero, you'll find that this has an increased tension. So that seems quasi-reasonable so far. Now let's consider the tension like over here, and the weight, the force diagram. So there's going to be a tension pointing this way towards the center of the circle, because that's the way the string is attached. The string can only exert a force in the, in the direction that it's attached and pulling, right? But the weight is still pointing down, which is fine. But in terms of the radial forces, we cannot include the weight here in the radial forces, because the weight is not pointing either towards or away from the center of the circle. So we would just have to say that, well, whatever this tension is at this point, we know what the acceleration is because it's moving in a circle, v squared over r. And so there you go. That the tension in the string at this point is going to be mv squared over r. And that's fine. Now things get interesting at the top of it, because the force diagram there, again, considering the forces in the radial direction, the tension is pointing towards the center of the circle. The weight is also pointing towards the center of the circle. And so instead of having a minus sign here, we're going to put a plus sign. Again, g is plus 9.8 in all the examples. And then because we have, because we're moving in a circle, the acceleration is v squared over r. So if we wanted to calculate the tension, we would say the tension is mv squared over all minus mg. And which is interesting because for some values of V, that would give you a negative tension. Is it possible, folks at home, for strings to have negative tension? Let's think about this for a second. What would it look like for a string to have negative tension? Well, you can pick things up. If I tie a string to something on the ground and pick things up, there's going to be a positive tension in the string, and that's how I'm going to be able to pick things up. Is there any way to have a negative tension in the string? Not really. I mean, the way I think about it is that I can tie a string to a doorknob and pull a door open, but I am not going to be able to tie a string to a doorknob and push it shut. That would be like negative tension, maybe. I don't know. But, so negative tension is not quite possible, which means that this only makes sense if the tension is positive. And so we can try to find at what velocity does the tension become zero, and that actually turns out to be the tension for which we need to, or that's the velocity for which we need to spin it faster than that to make sure that it goes all the way through the top without sort of, more or less flying like a projectile. So we can calculate what that is. So if we set the tension equal to zero, the mass cancels out. We end up with V needs to be greater than the square root of G times R. So that's how you figure that out. Now we don't really know V per se. We know that it has to be greater than this at the top. And we can, if it has to be greater than this at the top, it would make a lot of sense if it's much greater than this at the bottom, because it's going to go slower as it goes up. But we don't really know exactly what V is, which is okay. So maybe the problem would tell you it, or I don't know. You have to make some assumption. Now there's lots of variants of this problem. So in this video from, so this is from the Flipping Physics YouTube channel, which is excellent. You can kind of see how he's rotating the buckets more and more slowly, and eventually the water in the bucket starts to fall out, which is exactly the same calculation I just did. As it goes more slowly, eventually the normal force holding the water in becomes zero, and it starts to splash. But there's variants of the problem where you might not have thought of. So some of these variants do not necessarily involve going all the way through the full motion. So a kid on a swing is going back and forth like this. Typically the kid is not, going all the way around the thing. A pendulum, sort of like, in a grandfather clock, there's like one of these things going back and forth. We'll talk more about that much later in the course. We're going to talk about loop-de-loops later, water in a bucket. So there's variants of this problem. This is an active figure from the book, which was written in Flash, which probably only works on my computer at this point. Yeah, see this passive-aggressive warning saying Flash is going to stop working in a few months. So here is a person on a swing, and I think this is a nice demo. You can kind of set the initial angle, maybe set it back here, and then go ahead and press start. And it's nice that so it's not going all the way around the top, but what's interesting is that you can see they're illustrating the tension here. You can see the T there. You can see that the weight is always pointing down. There's always an mg that points directly to the ground. But what's interesting is that there is a component of that weight that is in the radial direction, and there's a component of that weight that is tangential to the motion, tangential to the circle that it's making. So it's a nice little animation. Now over here, this arrow in the middle, I would love it if they could write F net on this arrow, because this is really the net force, because they're taking the tension force minus the weight, and the result of that is really this capital F thing. And as the thing goes back and forth, you can see that there is a component of the force that is in the direction of the circle. So this mg sine theta is the only tangential force, and so this ft thing, ft for tangential, that's basically proportional to this mg sine theta, and as sine moves, it gets bigger and larger and smaller. And then this FR thing is basically the the balance of the two radial forces, and at the middle the tension is much larger than the weight pulling down, and so that sort of varies as it goes through the motion as well. So it's an interesting interactive. I'm not sure if the book actually has this as an interactive anymore, but it's a nice thing that kind of illustrates. Let's see. All right. There's another fun thing I wanted to show, which is this loop-de-loop. So this actually you can play around with. This is from physicsclassroom.com. And what I want to do is, maybe I can make this full screen, something like that. I really like this loop thing, which is pretty fun. So I can show the velocity vectors, show the force vectors. And so you can see the normal force on this little roller coaster becomes very large in moments where it's accelerating rapidly. So if you have this, these tight curves, the normal force is very large because it's, the car is sort of forced to accelerate at a rapid rate. What's interesting to me is that as it's going through the top, if you look carefully, you can see that the normal force is pushing down. I don't know if you can see that. I mean, these accelerations are much more pronounced. So, I mean, maybe I can try to pause this thing and move the things around a little bit, so it's not so wild. Do it like that, maybe. I don't know. Make it into more of a circle. So I don't know if that's going to help. But the point is that if you make this top thing high enough, eventually something weird happens, which is that if I can make these other ones taller, do it like this. Eventually something strange happens to the normal force. You see how the normal force had to go up? Like for a minute there, for a split second there, the normal force is kind of up there. So that's because this is sort of too high, if that makes sense. I can make this even more pronounced. I can sort of pull this up to here, and so it's kind of like when you look at the roller coasters and they have wheels on the top of the tracks, but there's also wheels underneath the tracks. And so this having the normal force go negative is kind of like those wheels are on the underside of the tracks, making sure the thing doesn't fall. Yeah, that one's really pronounced. You see how the normal force is pushing up? How can the normal force push up? Well, that's, again, it has to do with the fact that there's wheels on top and wheels on bottom. Make sure the thing just doesn't fall off. So that's kind of fun to play around with. Maybe I can close this thing so it doesn't eat up my processor. All right. I think I just talked about this. All right. So the next thing is from a nice YouTube channel that I'm going to show you. So you may just want to watch the video here if you're on your iPads or something. Before we jump into it, I want to say that they have labeled the forces in this thing. F sub r includes both the normal force, in other words, the force of the road on the car, but it also includes the friction force. So as the thing is going up the ramp, the wheels are pushing against the road, and so the road is helping the car go up the ramp, and so this F sub r that's illustrated in the diagram sort of goes more upwards than you might expect. If it was just a radial force, it was just sort of, the force towards the center of that circle. So anyway, that's the disclaimer. So F sub r is effectively more of a net force than a radial force, is what I'm trying to say. So let's watch this real quick.
Let's take a quick look